Welcome back, Algebra 2 students. In this video, we are going to be talking about logarithms some more, but we're specifically going to be referring to the graphs, how to graph logarithms, and more importantly, what the features of logarithmic functions are. So like what those graphical features are, things like domain and range, intercepts, increasing, decreasing intervals, etc. So before we get started, we have to think about what the parent function of a logarithm is, because when we talk about graphs, we talk about the parent or the most basic version of the function, and then we also talk about transformations of that function. So when I talk about the parent function, what I'm referring to is f of x equals the log base b of x. So there's not one specific base that will always be the parent. You can have multiple parent functions, sort of like we did for exponentials, where a parent would be 2 to the x, or 3 to the x, or 4 to the x. But it was the most basic version of that function because the exponent was just x. Here, this is the most basic version of the function because the log is being taken of just the x, okay? The base might change, but the log is just being taken of x. We are going to look at a couple graphs here. So I'm going to show you what approximately the graph of the log of x looks like. Remember, that's the log base 10, and this is something you could type in your calculator to look at. But that's going to look sort of like this. Okay. And I'm going to compare that to the graph of 10 to the x, which is the exponential. Remember that logarithms and exponentials are inverses. So an exponential function would look sort of like this. Okay, and you can see how those two are opposites of each other. And one other thing I want to point out is that you can see on the exponential, if you remember, we always have a horizontal asymptote that the function approached and never crossed. With a logarithm, we're always going to have this vertical asymptote that our function approaches and never crosses. And again, the reason that it is vertical this time is because those functions are inverses, so they are opposites of each other. Moving on here, we have a graph of a more specific labeled graph of the log base 2 of x. So this function is the inverse of 2 to the x. So that's worth noting that its inverse is the exponential function 2 to the x. Okay. And we're just going to go ahead and start looking at these features. So this is in fact a parent function because we are taking the log of just x. So the key features of this parent function are actually going to match up with the key features of all logarithmic parent functions. So things like domain, range, x-intercept, y-intercept, asymptotes, those are all going to match for all the parent functions. So when I have a parent function of the logarithm, the first thing I'm going to do is I'm always going to draw in that vertical asymptote. So like I said on the last slide, logarithms always have vertical asymptotes. The way I can draw this in is if you look at the bottom of the graph, where you see the part where it's basically just going straight up and down, well, it looks like it basically comes to the point where it touches the y-axis, but we know based on the function of the property, based on the property of logs, that a log isn't actually ever going to touch the y-axis. And that's because I can't have an x value of 0. I can't take the log of 0. I can only take the logs of positive numbers. So that's why this function is only on the positive x part of the graph. But with that being said, that means that I'm going to have an asymptote of the y-axis. Okay, and again, that asymptote is going to be on the same location for all of our parent logarithmic functions. Another thing that you will see in every parent logarithmic function is this x-intercept here. Okay, and those are really important. So those are actually the features I'm going to point out first over on the right, even though they are further below. So that point that I just highlighted in is 1, 0. So remember that the point 1, 0 is on the parent of every logarithm function. And so this is basically, oh, I don't know why I wrote that under increasing interval. Goodness gracious. This point is going to be on the parent. So when we talk about transformations and translating to the left or right or up or down, this is a point that you can move in order to figure out where the graph would go, as is the asymptote. So that asymptote here is for x equals 0. Remember that a vertical line is always going to be of the form x equals some number. And that is because as you have a line that moves up and down, the x value does not change. So our vertical asymptote here, it passes through the point 0, 0. As I look at any point on this line, like I could look right here, my x value is still 0. I could look here, my x value is 0. I could look all the way down here, my x value is 0 at all of those points. Okay, so the thing that is constant about this line is that x is always 0. So that's why you write it in the form of the equation x equals 0. While the asymptote might change, it might be translated to the left or translated to the right, it is always going to be a vertical asymptote, so our equation will always be of the form x is equal to some number. Okay. Now that I have those written out, those are sort of like the starting points for logarithmic functions, I'm also going to talk about the domain and range. So we have domain, which refers to the x values that the graph covers, and range are the y values. So basically the domain is what values can I input into this, which x values does the graph cover. As I already mentioned here, because we're taking the log of x and you can only take the log of positive numbers, my domain is not going to include any negative numbers or 0. Rather, it is starting right after 0. So if you look at my function, again, it doesn't start till right after the asymptote, and it starts right after the asymptote to the right of it. So it basically starts at 0, not on 0, so 0 is not included, it never touches 0, but it starts immediately following 0. So I have that parentheses 0, and then if you look over to the right side of the graph, we can see that it continues off the edge forever, so that means that my domain is from 0 to infinity. When I refer to my range, I'm looking at right the bottom and the top of the function. So I saw the function and I've sort of written over it, but this red line had continued down to give me basically a almost vertical line right next to the y-axis. So that means that this function is pointing down forever. So that means it starts at the bottom at negative infinity. And if I look at the topmost part of this function, which is over here, I see that this arrow is pointed mostly to the right, but also slightly up, which means that this is going to continue up forever as well. So since it starts at the very bottom of the graph, goes forever towards the top of the graph, that means that that point is that the range is in fact negative infinity to infinity. The next thing that I'm asked is the y-intercept. This is actually a trick question. Some people will be tempted, especially if you're not seeing everything I drew down here. You would be tempted to say like, oh, maybe it's down at like -4 or -5 or something, right? Like people are tempted to say it's like something down here. But remember, the reason we drew that asymptote in is because an asymptote is a line that my function never touches. So my line doesn't, or my function, my logarithmic function, doesn't ever actually touch the y-intercept because the y-intercept is an asymptote. So in this case, there actually is no y-intercept. Some log functions will have a y-intercept. For instance, if I were to translate to the left, you can see how this function would cross the y-intercept or the y-axis, so I would have a y-intercept, okay? But unless I'm translating to the left, that's not going to be the case. Right. And the last thing here is increasing interval. I don't have increasing and decreasing listed because I'm just kind of giving you the fact that this is an increasing function. But remember, the way you know if something is increasing or decreasing is basically trace that function starting from the left to the right, just like we read. And if my pencil is going up, which it is, that tells me it's an increasing function. The logarithmic function always increases or it always decreases, which means that it is increasing over the whole domain. So it will match the domain of 0 to infinity. It is increasing the entire time the function exists. Okay, and even if you hadn't already pointed out the domain, again, realizing that it starts increasing right down here at the leftmost part, and that is basically at 0. And then as we continue over towards the right, we can see how it continues to increase forever. Okay. So with that being said, we are going to move on from the parent function and apply what we learned there to some transformations of log functions. But first, I want to point out that the parent function, once again, I already said this, will always go through the point 1, 0, and it will always have a vertical asymptote of x equals 0. That means if you were to ask to graph the parent function of any of these, you can start by plotting that point and plotting that asymptote. Okay. And another thing just to note, this is the opposite of an exponential function, where the parent would have a point at 0, 1, and it would have an asymptote of the x-axis. So once again, just pointing out how inverses are opposites. Okay, so here I'm looking at my first transformation. This is a transformation of a function with a log base 2. As I said before, the different bases aren't going to change the function a whole lot. It's going to have the same general shape. It would have the same features. The only difference is basically the steepness. So you see how this is sort of like a softly curving function, right? Like as it sort of goes around this curve. If it was, say, a bigger base, let's say base 4 or base 10, what would happen is that we would have the same like general features, but the shape of the graph would look something more like this, right? Where it'd have a little bit more of a sharp curve over at the side. But with that being said, we're just going to focus on this one here. We're going to look at what this transformation is. So you can decide what the transformation is on a log function, just like any of those other functions we looked at. So the number that is being added or subtracted right after the x within the parentheses, that is going to translate right or left, whereas a number that would to be added or subtracted outside of those parentheses, not as part of the actual log, that would translate me up or down. Because here I have plus 2 in the parentheses, that is part of the log right next to x, that is going to translate me right or left. And in this case, because it's opposite to inside the parentheses, just like all our other functions, this is going to translate me 2 units left. So this is a translation of 2 units left. Okay. Now, just to confirm that I'm right there, I'm also going to look at this graph. They did give it to me, but I'm going to sort of approach it almost as if they didn't give it to me. Remember I said there were 2 things I wanted you to remember about the parent function. One of those was that the parent function goes through the point 1, 0. So the parent function would have gone through this point right here. So if I'm translating 2 units left, let's look and see if this makes sense. Well, that point, 1 unit, 2 units left. Oh, that does still land on my function. So that sort of makes sense, right? That I've now translated 2 units to the left. My x-intercept has gone 2 units to the left. Okay, oh, didn't mean to clear all that, but whatever. And then the other thing I had told you was that we have a vertical asymptote at x equals 0 for our parent. And I've now shifted this or translated this 2 units left. If you look where the asymptote is for this function, that right there is the line that we never cross. Okay, it's the line that the function approaches. So just wanted to point out again how that makes sense that this has been a transformation, a translation 2 units to the left. Now that we have all that information, and I sort of pointed out where the x-intercept and the vertical asymptote are, we can go ahead and start talking about the key features. Again, just because we already drew those, this is sort of the starting point. So I'm going to go ahead and start by writing in the equation for the asymptote and the x-intercept. So in this case, the x-intercept is at negative 1, 0, just looking at the graph to find that. And the vertical asymptote is of the equation x equals negative 2. And that's because it's a vertical line where every point on the line has an x value of negative 2. Okay. Moving on from there, I'm going to talk about domain. Just like my asymptote, my domain has essentially been translated 2 units to the left, which means instead of starting at 0, here it's going to start at negative 2. Or my domain is always just going to start right after that asymptote because my function approaches the asymptote but doesn't cross it. So my domain, my x values that this function covers, they start at negative 2 and goes to infinity. On the other hand, the range is looking at my y values, and I look how at the bottom of this graph, I essentially have it pointed down forever, and at the top of the graph, I have it essentially pointing up forever. So just like my parent function, my range is going to be negative infinity to infinity. And you will find this to be the case with all of our logarithmic functions. The next thing we're asked is the y-intercept, and just like I said in the last problem, if I translate to the left, you will in fact find y-intercepts. So looking at this problem, I can see that the function does cross the y-axis, and that happens at this point right here, and that point happens to be 0, 1. If this ever happens at a point and it's not like a perfectly even point that you can see on the graph, let's say it occurs at a decimal, the way you can figure out the y-intercept is you see how the y-intercept, when I cross the y-axis, the x value is 0. So you can always go into your original function and you can just plug in 0 for x and then evaluate that there. So in my calculator, I type log of 2 divided by log of 2, and I would find my y value of 1. Okay, because it's log base 2 of 2, we don't need to actually do that. But if it were to come out as a decimal, that is a way you can approach it. You can always determine the exact y-intercept, even if you can't see it on the graph. And then the last thing we're going to talk about is the increasing interval. Once again, this function is increasing for its entire existence. So its increasing interval is going to match the domain from the point it starts at -2 all the way for the rest of its life. As it continues towards infinity, it's increasing that whole time. So my increasing interval is from -2 to infinity. Okay. What should we do? Okay, I'm going to go ahead and do one more example before we go. This is an example of a transformation that has a horizontal and vertical translation. So you can see inside the parentheses, again, that shifts me right or left, and it's opposite day. So we have a translation. And again, I'm just going to abbreviate translation of 1 unit right and 2 units up. Okay. So what this means is, again, I'm going to think about starting with where my parent functions asymptote and x-intercept are. I know to normally expect a point right here and to expect an asymptote right here. So if I am translating 1 to the right and 2 up, as I move this point right, 1 to the right and then, 2 up. You see how that point transformed to the point that I just drew on the graph now? So that kind of confirms that we are correct about the transformation, and that is sort of this new location of that point. Okay. The other thing that we do is it was a translation of 1 unit right, so the asymptote will also translate 1 unit right. Now the vertical shift doesn't really affect the asymptote because if you move a line up or down, because it continues forever in both the up and down direction, that doesn't really affect it. So the only time the asymptote is changing is if you do translate right or left. But we did do that in this case. So my actual asymptote, which I'm going to draw in this other color, is going to be 1 unit further to the right. It's going to happen here at x equals 1. Okay. And once I have that, I'm just going to go ahead and erase the other ones so that you don't get confused. Notice in this problem, if you look at the x-axis, there is no clear x-intercept. The x-intercept, if it's not easily found on the graph, is actually a lot more complicated to solve for than the y-intercept. So I'm not actually asking you to find it in this problem. Again, the reason that that happened is because there is a translation up or down. So my x-intercept didn't like just shift right or left when the function also shifts up. It's just a different part of the graph that's crossing the x-axis. So it's not going to be convenient to find that x-intercept. With that being said, we're going to continue on to domain. Again, the domain has to match our transformation. So I translated 1 unit to the right, so my domain also translates 1 unit to the right, which means that instead of starting at 0, my domain starts at 1 and continues to infinity. Right? It starts at the asymptote of 1 and then continues the whole way off to the right out as I continue to infinity. My range, just like all the other problems, you can see this function, it goes the whole way down, it goes the whole way up. So my range is from negative infinity to infinity. Looking here, I translated to the right. So we've talked about how the parent function does not have a y-intercept. If I translate left, I get a y-intercept. If I translate to the right, I just move further away from the y-axis. My function still doesn't cross the y-axis. So there once again is no y-intercept. And then looking at the increasing interval, it is increasing again for the entirety of the domain. So from 1 to infinity. Okay, so this video is getting pretty long, so I'm pretty much going to wrap it up. I'm not going to do another example problem because every example is going to be relatively similar, but I do want to show you guys one other graph. Just looking here at this is a graph with a different base. So all of our other functions had the parent function log base 2 of x because they were logs of base 2. This example here has the base of 4. And again, I just want to point out that you treat it the same way. It still would have had the same, like the parent function still would have had the same asymptote, the same x-intercept. The only difference is that if you look at this graph, it's sort of like the steepness of this curve and the angle at which it sort of turns off to the right is a little bit different than in the example prior. So you can sort of see the contrast between those two. But again, the domain, the range, x and y intercept, asymptote, increasing interval, none of that is changing just because it's a different base. So if you see another base, you don't need to do anything different, which is why I don't actually need to solve this problem for you. So with that being said, this video is over because it was already getting kind of long. But at this point, you should be able to understand how we get the graph of a logarithmic function, how you get the graph of transformations of the logarithmic function, as well as how you can determine the key features of a log function.